Welcome to today's Explainer, where we're going to embark on a seriously incredible geological journey. We usually look out at a landscape and see something static, right? Something permanent. Well, today, we're going to flip that perspective entirely. We are looking at the unseen forces beneath our feet. We'll be tracing this wild, fascinating path from microscopic chemical battles hidden deep inside stones, all the way up to macroscopic, earth-shattering seismic events. Okay, let's dive right in.
So think about it for a second. Is the ground beneath your feet actually as solid as you think? It's a paradox we rarely consider. We build our homes, our cities, literally our entire lives on this basic assumption that bedrock is completely immovable. But what if I told you that even the most structurally stable regions on Earth harbor these hidden, microscopic weaknesses that eventually dictate massive seismic dangers? To really understand how a supposedly safe zone can just suddenly shake, we have to completely scale our perspective, going from the micro all the way to the macro.
Here's the roadmap for today. 1. Chemical battles inside rocks. 2. The 6 layers of granite. 3. How rocks bend and break. And 4. The earthquake risk paradox. Let's get to it.
All right, first up, chemical battles inside rocks, the invisible war.
Believe it or not, there is an active, totally invisible war happening every single second right at the Earth's surface. We tend to think of weathering as just, wind and rain mechanically eroding things away. But chemical weathering, that is much more subversive. It involves water, oxygen, and atmospheric acids actively decomposing rock minerals at the atomic level. Now, the very first weapon in this chemical war is dissolution, which is also known as carbonation. When carbon dioxide from the atmosphere mixes with everyday rainwater, it actually forms a weak acid called carbonic acid. So when this slightly acidic water comes into contact with minerals like calcite, which you're going to find heavily in rocks like limestone or marble, it doesn't just chip away at them, it completely dissolves them into solution. The rock simply vanishes, carried away by flowing groundwater.
Then we have hydrolysis. This is where things get really interesting. Here, the very ions in water, hydrogen and hydroxide, react directly with silicate minerals. Imagine a really tough, hard mineral like orthoclase feldspar. Through hydrolysis, water chemically breaks it down, basically leaching out the soluble potassium. And what's left behind? It's not feldspar anymore. It transforms into a completely new, incredibly soft clay mineral called kaolinite. Literally, a hard stone turns to soft clay right from the inside out.
And our third chemical attack is oxidation. Now, you're definitely familiar with this one as rust. When atmospheric oxygen reacts with iron-bearing minerals hidden inside rocks, minerals like olivine, pyroxene, or biotite, the iron oxidizes. It forms iron oxide minerals like hematite. This process absolutely wrecks the structural integrity of the entire rock mass, stripping away its strength and leaving behind that highly characteristic reddish-brown coloration that we so often see on exposed cliffsides.
Okay, moving on to part 2, the 6 layers of granite, anatomy of the Earth.
So what exactly happens when this unseen chemical war rages on for, say, thousands of years? Well, the rock begins to decay in some surprisingly predictable stages. By looking at granite slopes in tropical environments like Malaysia, engineers and geologists can actually map out this decay into a classic 6-layer profile. Based on British standard guidelines, weathering progresses from the ground surface all the way down to the deep bedrock. Structurally, it moves from fully matured residual soil up at the very top, which is grade 6, down through varying degrees of decay until we finally hit grade I at the bottom. And grade I? That's your pure, pristine rock.
Let's break down these extremes a bit, step by step. Up at step 1, grade 6, is residual soil. The original rock texture is just utterly destroyed. It's basically just a mass of soil that you can easily remold with your bare fingers. As we move down to step 2, grades 4 and 3, we find a bit of a mix. More than half the rock might be soil, with these isolated, unweathered core stones left behind. It's kind of crazy, but if you strike a grade 3 rock with a geological hammer, it actually gives off this distinct, hollow sound because of all the internal decay. Finally, at step 3, we reach grades 2 and 1. By the time we hit grade I, we are looking at pristine, fresh rock. 0 signs of chemical discoloration, and it rings cleanly and sharply when struck by a hammer.
All right, part 3, how rocks bend and break, massive structural shifts. So, we've seen how chemicals weaken rocks, but what happens when massive tectonic pressures are applied? There are 2 primary ways rocks react: ductile versus brittle behavior. Deeper down in the Earth's crust, temperatures and confining pressures are incredibly high, and the strain rates are really slow.
Under these conditions, rocks exhibit ductile behavior, meaning they undergo permanent plastic deformation. They continuously bend and flow without actually fracturing. But near the cooler surface, where the pressure is lower, rocks reach their elastic limit and they rupture suddenly. This instantaneous failure is what we call brittle behavior. Now, the real kicker is what happens right after that sudden rupture. Brittle failure produces two very distinct outcomes: faults and joints. A fault is a brittle planar fracture where there is visible displacement or shearing movement. The rock blocks have actually physically slid past one another. A joint, on the other hand, is just a simple tensile crack within the rock mass. The rock has split, sure, but there's no measurable relative movement or offset between the two sides.
On the flip side, what happens during that ductile plastic deformation we talked about? We get folds. Specifically, synclines and anticlines. A syncline is this down-arched, trough-like fold where the youngest sedimentary rock strata are squeezed right into the center of the core. An anticline is the exact opposite. It's an up-arched, dome-like fold where the limbs dip outward, leaving the absolute oldest sedimentary rocks exposed at the very center of the fold core.
Bringing us to our final section, the earthquake risk paradox, danger in the safe zone.
Now we can apply everything we've just uncovered to a really high-stakes scenario that catches a lot of people off guard: the geography of Peninsula Malaysia. See, it's an intraplate setting, located right on the structurally stable interior of the Sunda Plate. It is positioned far, far away from active plate boundaries like the Sunda Trench. By all traditional logic, a stable interior means safety, right? And yet, this region remains at significant risk for seismic activities. It's a huge paradox. Why on earth does the stable ground suddenly shake? Well, the answer basically comes down to two major geological risk factors that are kind of hiding in plain sight. Number one, the reactivation of ancient fault lines. And number two, far-field seismic wave amplification. Let's look at how these two mechanisms completely bypass the supposed safety of the stable plate interior.
Let's tackle that first factor. Peninsular Malaysia is actually crisscrossed by these prominent ancient regional shear zones and faults, like the Bukit Tinggi, Kuala Lumpur, and Lepas faults. Now, they've been dormant, but there is an ongoing collision between the Indo-Australian and Eurasian plates nearby. Over time, that massive tectonic stress accumulates and it ripples inward through the crust. Eventually, it finds those brittle fractures we discussed earlier and completely reactivates these ancient dormant local fault lines, triggering localized, shallow earthquakes right in the middle of the plate. There's no escaping the stress.
And then there's the second factor, far-field seismic wave amplification. This is where our knowledge of decayed rock and soil really comes into play. Major subduction earthquakes generated along the active plate margin in Sumatra send out these long-period seismic waves over vast, vast distances. When those far-field vibrations finally reach coastal cities like Kuala Lumpur or Penang, they encounter deep deposits of soft quaternary alluvial soil. And instead of dampening the vibration, these soft soil layers actually amplify the ground motion. They act almost like a giant bowl of jelly. This causes noticeable and sometimes really dangerous structural shaking in high-rise buildings literally hundreds of miles away from the earthquake's epicenter.
It's pretty wild to think about, right? We've traveled from microscopic water molecules leaching potassium from solid rock all the way to ancient structural fractures being violently jolted awake by distant colliding continents. It all leads us back to this incredible paradox. If even the stable interiors of tectonic plates can suddenly rupture or amplify distant seismic waves, is any ground on Earth truly unshakable? The chemical weaknesses and tectonic stresses of our planet are always at work, right beneath our feet. Thank you so much for joining me on this explainer. Keep questioning the world around you, because honestly, nothing is ever as static as it seems.